We're about 10 seconds away from 5:30. All right, so it is time to get started. So today's lecture is going to be about binary subtraction and also comparison. So those two things are essentially the same thing inside the processor. So what we'll do is we're going to go through some subtraction stuff first, just to make sure that you guys still remember your binary subtraction logic and the equations and whatnot. And then we'll proceed to talk about how do you know whether x is less than y. Okay, so that's going to be what we'll be talking about today. The lab is going to be on the same material. So that means it's kind of important to make sure that you understand the material in the class in order to get the lab done. All right. So for the most part, I'm going to, oop, that is not what I want to do. Okay. All right. So what I want to do is to use my tablet here. Instead of using the whiteboard for a few reasons, this is now recorded. And two, I don't have to smell the fumes of the dry board markers, which I actually quite enjoy. All right. Yes. Hmm? Is that a welcome? Nope. This is a super note. It's a super note. Essentially it is an Android system, but they have their own user interface on top. So it's not entirely, Android compatible, but for the most part it is. All right. So what we'll do is we're going to start with some binary subtraction. So I will use examples where I'm going to use it again later. So we'll start with 0, 0, 0, 1 minus, oh, I don't know, 0, 1, 0, 0. Okay, that's fine. Okay. So this is a base 2 subtraction. We got x, we got y, we got q, we got t because it's a subtraction, and then finally we got d as the last row. All right, so I'm not sure how much you remember about binary subtraction. You should probably know how to do this already. So I'm not going to quote the actual equation because you should know how to do it. All right, so between the x and the y to compute the q, it is what we call exclusive OR, okay? So exclusive OR means, if both x and y are the same, then q is going to be a 0. If x and y are different, q is going to be a 1. So this is going to be a 1, this is going to be a 0, this is going to be a 1, and this is going to be a 0. And by the way, the symbol of exclusive OR looks like a plus with a circle around it. Okay? And this is what we talked about when we talked about binary addition and subtraction. So you probably need to make sure that you read all the reading material because it is actually in the reading material over there. So the T row is a little bit like the K row. 1 minus 0, so there's an implicit 0 here. So 1 minus 0 does not have a borrow. 1 minus 0 also does not have a borrow. So the borrow, at this particular point is going to be a 0. 0 minus 0 does not have a borrow. 0 minus 0 does not have a borrow. So we have a borrow of 0 over here. 0 minus 1 has a borrow, so we immediately put a 1 over here. And then last, we have 0 minus 0 does not have a borrow, but 0 minus 1 does have a borrow, so we put a 1 over here. Now we get to the D row. The D is really just the exclusive OR between the Q and the T, which is also what the R function does for base 2. So now we have 1, 0, they're different. We put a 1 here. 0, 0, they are the same. We put a 0 over here. 1, 1, excuse me, 1, 0, they are different. We put a 1 over here. 0, 1, they are different. We also put a 1 over here. So do we have any questions about binary subtraction? So what equations have we talked about in terms of binary subtraction? So this is for you to investigate. You have to remember Q of I is expressed as something. You have to remember t of I plus 1 is expressed as another expression, and you also have to remember d of I is also expressed as some kind of equation. So that is what you need to do, is to find out, how these are expressed. They are in the notes, okay? Which I think they should be in your own notes too, just so that it is easier for you to find in the first exam. All right. So is this ringing any bell? Okay. Have you guys been spending 2 hours of time to study for this class for every hour that you're in this lecture hall? Okay. Well, then we know what to do, right? Okay. Because for this class, that is almost essential. Okay. Except for a few people in this class, I would say spending 2 additional hours for each hour in lecture is, is a reasonable estimate. All right. But today's lecture is not about binary subtraction. Okay, that's a topic that we talked about 1 week ago. Okay, at least 2 classes ago. So today's lecture is about how do we know whether x is less than y. Okay, so we'll go through a few examples. Okay, because they illustrate different boundary cases. All right, so we'll go through another one, which is um, let's see. Oh, this is a good one. 1000 minus 1. That's an easy one. Okay. So we have x, we have y, and this time I'm going to go through this a little bit quicker. Okay. So exclusive OR 1001, and then this is usually a 0. 0 minus 1 has a borrow. 0 minus 1 has a borrow. 0 minus 1 has a borrow. And then finally, 1 minus 0 does not have a borrow. 1 minus 1 also does not have a borrow. We put a 0 over here. And then on the D row, we also use exclusive OR. 1 minus 0 is a 1. 0 minus 1 is a 1. 0 minus 1 is a 1. 1 minus 1 is a 0. Okay? All right. So we are, once again, today's lecture is not about the binary subtraction mechanism because that was discussed about 2 classes ago. So if you need to brush up on binary subtraction, you're going to have to go back to, you know, 2 lectures ago. Unfortunately, everything is recorded, and I'm just double checking to make sure that this is also getting recorded. So you can go back and kind of revisit, the lecture by watching the video again. The nice thing about watching a video is you can pause. Okay, you can just kind of hit the pause key, try to think, just kind of absorb the material. Once you have absorbed the material, hopefully writing your own understanding on a piece of paper so that you can kind of keep it with you. Then you can proceed, unpause, and then continue to the next section of the lecture. How many people have watched the videos? Nobody. Okay, someone. Okay, very good. So I would say it is a resource that is available to you, but it is not a resource if you don't use it. Okay, so that is also up to you to decide how you want to use the available resources. All right, so we're gonna go through a few more examples. Let me pick another one, which is this one here. So we have 0, 0, 10 minus, let me see. We can do a 1, 0, 0, 0. Okay. So this is x, this is y, q, t, and then finally we have d. 0, 0. So this is a 0, this is a 1, this is a 0, this is also a 1. 0 minus 0, 0 minus 0 has no borrow. 1 minus 0, 1 minus 0 does not have a borrow. 0 minus 0 does not have a borrow. 0 minus 0 does not have a borrow. So we put a 0 here. 0 minus 1 does have a borrow. So we put a 1 over here. And then finally, we get to the D row, which is 0 minus 0 is a 0 as a single digit difference. 1 minus 0 is a 1. 0 minus 0 is a 0. 1 minus 0 is a 1. All right. And I believe there should be one more case. Yep, there's one more case. So we're going to go with minus 1, 1, 1, 0. Put a 0 here, put a 1 here. So here's xy, qt, and then finally we have d. 0 minus 1 has a single digit difference of 1. 0 is over here, and t0 is usually assumed 0. 0 minus 1 has a borrow of 1. 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 So the result is going to be 1, 1, 1, 1. There we go. All right. So the next question is, well, this is all just subtraction, right? So how do we, how can we tell whether x is less than y? All we need is to see whether a number is less than another number, because from that, I can rederive all the comparison operators. In C++, they're actually called relational operators, but it's okay, okay? Really, it's just a name. So I'm going to use this slide to illustrate why we only need to know less than. Okay, so let's say we need to know whether x is less than y. Okay, that's a given. Okay, we have to rely on whether we can tell whether x is less than y. So x is less than y does not require anything. We don't have to do a single thing. So if we have to figure out what is y, oh, I take it back. Undo, undo, undo. Okay. So if we have to tell whether x is greater than y, that's easy because this is true if and only if y is less than x. In other words, I just have to flip the two sides and greater than becomes just less than now. Okay, so now the next one is x does not equal to y. Okay, so if we need to figure out whether x and y are just different, I don't really care which one is greater. That means I can now translate that to x is less than y or y is less than x. Okay, does that make sense? Okay. So what if I want to tell whether x and y are the same? Well, I mean, since we already know how to tell whether x is different from y, we just have to negate it. Okay, so we just have to put a negation over the same thing that we have in the previous row. Okay, there we go. I think we are missing 2, right? Less than or equal to versus greater than or equal to. So we have less x is less than or equal to y. That just becomes, it is not the case that y is less than x. Does that make sense? Yep. Say again? Well, we don't know how this is going to work at the transistor level yet. Okay, but all I want to do right now is to say if you can tell whether x is less than y, that's all we need, because the rest can be derived from just knowing whether x is less than y, or the left-hand side is less than the right-hand side. Okay, so we got one more. So we have x is greater than or equal to y. That just translates to it is not the case that x itself is less than y. Okay, so this is telling you that C++ has a lot of redundancy because out of all the relational operators, this is the only one that you actually need. The other ones are nice to have, okay, but you don't need it. It's just like NAND can be used to implement not and or. So if I want to make a minimalist programming language, it will only have NAND as the only logical operator and only has less than as the relational operator. That would be quite painful to read the code, but it is possible. As usual, just because something is possible does not mean it's a good idea. All right. So are we good so far? Are we understanding why less than is all we need? Okay. So now we go back to the previous binary subtraction example, and I'm going to get rid of this portion here because it's really not part of the discussion that I need today. All right. So with this one, we are going to look at this from the perspective of signed versus unsigned. Okay. So we say, okay, oh, this is also a good time to go back to the notes just a little bit because I need to kind of show you guys a equation. So let me go back to the module, which is about binary comparison. I believe last time I already said that we would be talking about binary comparison today. So hopefully you guys got a chance to read ahead. Okay. Um, so there are a few things that are kind of important, and they're circled in green. Okay. So I think this is like 2 semesters ago. I decided, well, why don't I just kind of circle the stuff that is actually important, so that I save you the trouble of having to circle it. But this is just an example. I'm not going to do this for all my reading material. So VU of XM. Okay. So if you have not read the notes, okay, this might take a little bit of time. So VU means the value interpreted unsigned. Okay, that's what the U is, unsigned. V stands for value. X itself is a bit pattern, which means it's a binary number, a bunch of zeros and ones. And then M is we only want to interpret up to M bits. So it basically tells us which portion of the bit pattern X do we want to interpret as an unsigned number. Is that okay? So the sigma notation should look a little bit familiar because we talked about this in base conversion already. Essentially, it is the same thing as base conversion, except I starts from 0 instead of negative infinity, and then it goes all the way to just m minus 1 instead of positive infinity. So I'm just limiting the scope of which digits should I look at. But because it is also in base 2, so I don't have a b to the power of I, instead it is 2 to the power of I. So do we have any questions about the first sigma notation? It's really the same thing as base conversion that we have been talking about. This one is not tricky. The second one is a little bit tricky. It is VS, okay? It is VSXM, which means we are looking at the value interpreted signed. Okay, that's what the S is for. It is signed instead of unsigned. And we are also looking at the bit pattern X, and we only want to interpret up to M bits. So the parameters are specifying pretty much exactly the same thing, but the way we calculate is a little bit different. So you can see there's a sigma notation, but in the sigma notation, I only goes from 0 to m minus 2. It doesn't go all the way to m minus 1. It goes up to m minus 2. The expression inside the sigma notation is still the same, x subscript I times 2 to the power of I. So that part has not changed. So what are we going to do with x subscript m minus 1? Well, it's pulled outside, and instead of an addition, we have a subtraction here. In other words, the most significant bit, which is the leftmost digit of the m bits that we are talking about here, is subtracted. Okay, if it specifies a 1, we are subtracting the corresponding power of 2 instead of adding that corresponding power of 2. So that's the only difference between VU versus VS. Is that okay? All right. So we're going to apply these to the example that we have been talking about. Okay, so let me go back to the tablet and then we'll talk about that. Okay, so what we'll do is we're going to say, okay, what about VU? So we're going to go for unsigned first. So what is VU X4? X only has 4 bits, so I can only go up to 4. So what would that be? Let's see. 1 times 1 plus 0 times 2 plus 0 times 4 plus 0 times 8. I think that's just 1. Is that okay? What about VUY4? Okay, I'll let you guys quickly come up with that number. 4, that is correct. How about VS? VSX4? The only difference is what we do with the most significant bit. But if the most significant bit is a 0, then it doesn't make any changes. So this is still a 1, and the other one is still just a 4. Oops. That is why Okay, so this is where, both x and y, whether you look at it as a signed number or an unsigned number, they are the same. They represent the same values. Are we good so far? All right. And can someone tell me what is borrowing? What does it mean? When do we need to borrow? I'm looking at the most significant borrow bit here. What is the one here indicating? No, well, I mean, sort of, but not exactly. It means x is less than y. That's why you need to borrow. Okay, so we look at this little bit here, and we go like, maybe it has something to do with knowing whether x is less than y. So we'll go back and talk about that. And before we do that, we're going to look at this one. Okay, VU x4. This time it is what? What is the unsigned value of 1000? That is correct. And what about VU y4? That's an easy one. That's just one. What about VS x4? -8. Very good. Okay, very good. And then VS x y4 is still a 1. Okay. So this is where, remember, when you guys asked me, whether a certain bit pattern, I think it was what, 1101 or 1100? I think it was 1100. Whether 1100 means -4 or whether it means 12, right? And then I said, why do you care? Because you are not telling me what you're doing with those 4 bits. So I cannot tell you what you're supposed to do to interpret those 4 bits. But when we are comparing, it does matter because 8 is less than 1 is false. On the other hand, -8 is less than 1 is true. So once you know that you are comparing the 2-bit patterns and you know whether it is, then it matters whether it is supposed to be signed or unsigned. Does that make sense? So I hope this helps to answer the question that some of you might have from 2 weeks ago. Okay, when we talk about base, no, just Tuesday. Okay, because we only talked about the signed representation of values on Tuesday. So this definitely has something to do with signedness, of a number. All right, so next page, same thing. Okay, so we have VU x4 is a 2 this time, and then we have VS y4, that's also a -8. Oh, okay, I take it back because I only do VU over here and then VS later. I think this one is a almost a duplicate of the other one, so that's okay. We'll deal with it later. Okay, so VU y4 is an 8. Oh, it's reversed. Okay, the XY order are reversed. So VS x4 is also just 2 here, and then VS y4 is -8 this time. Okay, just one more to go. This one here. So VU x4 is 14, VU y4 is 15, and then VS x4 is, what is it? -2 is correct, okay? Because what we are doing is we are adding 0 times 1 plus 1 times 2 plus 1 times 4 minus minus 8. Okay, so that's why this is -2. And then VS y4 is -1 because we are adding. This is a 1, this is a 2, this is a 4. So 1 plus 2 plus 4 is 7. But this means we have to subtract 8 from 7, and therefore we have -1. Are we good so far? All right. So remember earlier I said, the B, is really useful. As it turns out, it really is, well, not B. It's T of 4 in all of these cases. So T of 4 is this, what we call You can call it a bit, which is a binary digit, but in the context of what we are talking about here, I call it a flag. In other words, it is an indicator of something by itself. Okay, so we call it a flag. It is called the B flag for borrow, the overall borrow. So in this case, this is a 1, and a 1 means your x is less than y in an unsigned way. So it's 1 less than 4. Okay, that works, right? So we look at this B over here, or this borrow flag. Since it's a 0, it's telling us that x is not less than y in an unsigned way. 8 is not less than 1. That works out. Okay, let's look at the next two examples. So in this case, this one here is telling us that 2 is less than 8. Remember, the borrow flag is only useful for unsigned interpretation. And then finally, we have this one, this case down here. We have 14 being less than 15, and the B flag is in fact a 1. So it is matching all the cases. It all works out. In other words, okay, going back to my notes, because I want to show you where in the notes you can find the conclusion of all of this. So if you go back to the notes, it is also in green. It says right here, okay, in a binary subtraction of two m-bit patterns, x minus y, p of m equals to 1 if and only if vuxm is less than vuym, assuming t0 is a 0, which matches all four cases that we have been talking about. Is that okay so far? Does everybody understand what the green rectangle is saying? So forget about how it is derived, but what is it saying? Okay, I will spot check a few things. Does everybody understand what is T subscript M, which is T subscript 4 in the four examples that I have presented? M is the number of bits, so T of M is the borrow bit that is kind of hanging on your on your left hand side. Okay, are we doing okay so far? Because the nomenclature, which is the way we name things, is really important. Okay, I try to make it very systematic from the beginning of the discussion so that when I refer to T of something, it is very specific, referring to the fourth row in a binary subtraction table. Are we still doing okay so far? All right. And obviously, this one also relies on VU, that we have just defined earlier. But VU is the same thing that we have already talked about when we talk about base conversion. So this one should not be very surprising. Okay, are we okay so far? All right. Yes. T0 does not have to be a 0 when we want to stack. Okay, so let's just say that we make a 4-bit subtractor. Okay, so what if you have 8-bit numbers or 16-bit numbers that you need to subtract? So the T0 is what is allowing the Tm of the quote unquote previous subtractor to become T0 of the next subtractor. So this way you can stack the 4-bit subtractors in order to perform a wider subtraction. Yep. But to us at this point, it is always 0. Okay, at this point. All right. And because there might be people who are wondering why does it work? Okay, so the most intuitive answer to why this works is simply because the borrow is a 1 if and only if the first number, it is called the minuend, is less than the second number, which is called the subtrahend. That is why you need to borrow. Okay, so that's the most intuitive way to understand why if and only if Tm is a 1, ytm equals to 1 if and only if vuxm is less than vuym. Okay, so for people who are looking at this and thinking, I cannot possibly remember all the definitions of VU, um, and T of M, and so on, that means reading ahead can be helpful. Okay, because if you're looking at this the first time, you're going like, okay, I cannot possibly make use of things that we just defined earlier. So writing this down can be helpful too, because you can then look at your own piece of paper instead of looking at the screen. And once I scroll this off the screen, you can't see that anymore. Okay, so it is always helpful to have your own notes. You can print this out, okay, bring it to the class if that is what you want to do, or you can put this on your iPad or your laptop computer. So when I'm talking about this and scroll around, you can fix your own screen to a certain portion of the notes. So all of those are doable things. So I can tell you that section 3.1 is useful, but only for people who want to go through the proof. Okay. If you have taken CISP 440 already, then the proof, which is section 3.1, should be somewhat readable. Okay. It may not be the easiest to read, but it should be somewhat readable. And this is the rigor proof of why T of M is an indicator of whether the unsigned value of X is less than the unsigned value of Y. Why the T of M itself is already sufficient to tell us whether X is less than Y. Now, will I test you on the proof? The answer is no. So for the most part, if this part here does not appeal to you, you don't have to read it. Okay? So that means we can skip a bunch of stuff here and go all the way to signed less than. Okay? So now we are looking at signed less than, and we are going to basically say instead of looking at VU, we're looking at VS now. And VS can be negative. So in that case, the B flag is no longer sufficient. So let me show you why I said the B flag is not sufficient or it doesn't work for signed numbers. So we go back to the examples that we have already worked out. And this time we are looking at the signed interpretation, which means we're looking at, in this case, it is still a 1 and a 4. So it would seem that the borrow flag is still working. However, if you look at the next example, the borrow flag is a 0, which is indicating that x is not less than y. But in this case, vs of x is -8. It should be less than 1. So that means the borrow flag is not working the same way as it's not working for signed numbers the same way that it works for unsigned numbers. If you need more convincing, here we have another example. There's a 1 here, and in the unsigned interpretation, 2 is in fact less than 8. So it works out just fine. But in the signed interpretation, 2 is less than -8 should be false. So that means T of 4, excuse me, T of 4 in this case is not telling us the correct answer. So that means, it is, I think this is enough proof to show you why T4 is not useful for signed comparison. Is that okay? All right. So if that is not sufficient, what are we going to do? Well, what we'll do is we are going to look at the math of subtraction and comparison. So what we are doing is we are looking at this part here. So D as a row is the difference. As a difference, it equals to x minus y. Does that make sense? Okay. So D of m minus 1 is a 1 if and only if the sign interpretation of x is less than the sign interpretation of y. And why is that? It's because of the earlier part here. If x is less than y, x is less than y if and only if x minus y is less than 0. Does that make sense? It is an inequality. If I subtract y from both sides, then the left-hand side becomes x minus y, and then the right-hand side simply becomes 0. But what is x minus y? It's our d, okay? It's the difference. So that means if x is less than y, then d is negative. But how do we make a number negative? How do we make a binary number negative? The most significant bit has to be a 1 because that's the only way to subtract something from the earlier parts. Okay, does that make sense? The most significant bit, which is bit m minus 1, is all. That's why it's also called the sign bit, because that one single bit will tell us the sign of the value that is being represented. If the sign bit is a 1, the value is negative. If the sign bit is 0, the value is non-negative. Are we doing okay so far? Are we linking and associating all the points? Okay, all right. So that should work, except it does not work all the time. So I will show you why it is not working all the time. So getting back to our example, okay? So what we are now looking at is the sign bit of the difference. So the bottom row, or the row number 5, is the difference. This is the most significant bit. So we are now focusing on just the sign bit of D, and we want to see how that is or is not working. All right, so we get back to this example here. So we look at this sign bit here. It is a 1, which means the difference is negative. Well, if the difference is negative, it means x is less than y. So we come to the same conclusion as earlier, that 1 is less than 4. That's cool. It works. Okay. But in the next example, it doesn't work. Okay. Because you can see that in this case, the sign bit of the difference is a 0, which means the difference is non-negative. If the difference is non-negative, it means, even from a signed perspective, y x is less than y is false. But obviously, negative 8 should be less than 1, so that means, okay, that doesn't seem to be working. And then we look at the next examples, the next page, this one. So now we look at this, and we look at the sign. We go like, okay, since the sign bit is a 1, that means the sign interpretation of x is less than the sign interpretation of y. But that is not true either, because 2 is not less than negative 8. In other words, the sign bit somehow is not working correctly. Okay? And then for the last one, the sign bit works again, because in this case, the sign bit is a 1, which tells us x should be less than y. Negative 2 is less than negative 1 is true. So what is going on here? Okay, because sometimes it works, sometimes it doesn't work. The math tells us that it should work all the time. But when we actually look at the implementation, sometimes it doesn't work. So what we need to do now is to really just look at the sign of xy and d itself. Okay, and you will start to notice that sometimes the sign of the difference doesn't make sense. So we're going to look at the first one. Okay, um, this is a non-negative value minus a non-negative value. Okay, we can look at this one too. So if you subtract a non-negative value from a non-negative value, and the result turns out to be negative, can that happen? Yeah, it can happen. 1 minus 2 is negative 1, right? I mean, so it can happen. Not a problem. But when you look at this one, it doesn't make sense, because this time you are subtracting a non-negative value, because the sign bit of y is a 0, from a negative value, because x has a 1 as the sign bit. But the result, which is the difference, is non-negative. Does that make sense? Let me say that one more time. You start with a negative value, you subtract from it a non-negative value, but the result turns out to be non-negative. Does that make sense? In other words, you look at negative 8 minus 1, and somehow the result is positive. Does that make sense to you? Does not make sense to you, right? So we're going to say, question mark, right? That's why I put a question mark here. And then on the third case, it also does not make sense, because we start off with a non-negative value, we subtract a negative value, the result should be non-negative. But somehow it is negative. So we have a problem with this case too. But for the last case, it makes sense again, okay? Because this time we start off with a, no, a negative value, we subtract a negative value from a negative value, the result turns out to be still negative. Can that happen? Yeah, it can happen. It can be positive or negative in this case. So now we have to really take a look at what is Vs of D, okay? Because exactly what we are looking at here. So Vs of D for this time is what? This is also a good chance for you to practice the Vs function because it is actually useful. You have to add up the rightmost 3 bits, or the powers of 2 of the rightmost 3 bits, and then subtract, the power of 2 represented by the leftmost bit. So what would that be? -6, because it is 0 plus 2 plus 4 minus 8. So this is -6. So when do you get 2 minus -8 being -6? You don't. Okay. So now the question is, how did this happen? Okay. But before we go back there, we're going to take a look at the other case where it also does not make sense. So in this case, VSD4 also does not make sense because that is just 7. -8 minus 1 should have been -9, and yet we are now having, we just have 7. So the question is, how did this happen? So to explain this, I'm going to go back, I'm going to redraw the number circle, okay, which I think most of you probably have copied already, which makes the lab on Tuesday super easy if you already have that. All right, so we are going to take a look at the number circle, okay. Okay, here's the number circle. We got 0, 1, 2, 3, 4, 5, 6, 7. On the other side, we got -1, -2, -3, -4, -5, -6, -7, -8. Those are all the values that you can represent by looking at a 4-bit pattern as a signed value. This is it, okay? This is the entire range. So the question is, what if a subtraction is causing this to cross the border right here? Okay, this is the border that I'm looking at. Okay, let me put a dotted line here. So if you try to add 1 to 7, what happens? Because adding means you are turning the needle in a clockwise fashion. So if you add 0 to 1, if you add 1 to 0, it's all cool. We just point to 1. If you're adding 2 to 3, we start here, and then you just add 2, and it ends up pointing to 5. Not a problem, right? But if you're already here, which is 7, and you're adding 1 to it, it becomes -8. Now that's because you're out of range. Yes, it is overflow. Yep. This crossing that dotted line is called overflowing. Okay. And it's also called, that's why we have the O flag to indicate overflow. Subtraction can also cause overflow. Okay. So normally when we are subtracting, we are turning the needle in a counterclockwise fashion. So let's just say that you start with 1 and you say, I want to subtract 3 from 1. So you have to turn counterclockwise 3 times. 0, -1, -2, all is good. Not a problem, right? But what if you start at -6 and you say, I want to subtract 4 from -6? Then it goes like -7, -8, 1, 7, and then the 6. It crossed this dotted line and we have an overflow. Is that okay? Does everybody kind of at least visually can tell what an overflow means? It means when you turn the needle in a subtraction or an addition, it crossed that dotted line. All right. So the reason why we have this little issue here is because -8 is really the most negative value that you can represent using only 4 bits. That's it. Okay, you cannot go more negative than -8. And 7 is the most positive number that you can represent using only 4 bits, interpreted signed, and that's why we have -8 on one side as the lower bound, and then we have 7 on the other side as the upper bound. Anytime you have a result that is exceeding this range, you have an overflow. Are we good so far? All right. So from the intuitive perspective, we can look at this little diagram and go like, okay, now we understand why we have overflow. But from the perspective of the processor, how can it tell that there's an overflow situation? Well, the overflow situation happens when the sign of D does not make sense. Let me say that one more time, which usually means it is important. Okay? If it's not important, I'm not going to say it again. When the sign of the difference does not make sense with respect to the signs of xy, you have an overflow. All right? So I would use two examples and then we'll get to the truth table. So in this particular example, does the overflow make sense? The x is non-negative, y is non-negative. The difference between x minus y is negative. Can it happen? Yeah, it can happen. 1 minus 2 is -1. Okay, it can happen. In this case, it does not make sense. Okay, because in this case, we have a negative value and you subtract from a negative value a non-negative value. And then we somehow end up with a non-negative value. That should not happen. Okay, so we are going to use only those 3 bits to help us decide whether an overflow is happening or not. Okay, so I'm going to, I guess I can circle this time, which 3 bits we're looking at. We're looking at x3, y3, and also d3 in this case to determine whether there's an overflow situation or not. All right, so this is what we're going to do. But looking at the example is not systematic. Okay, what if I forgot about a case? Okay, then you go like, well, then we don't know whether the method is going to work or not. So what we'll do is we're going to use a very systematic way to process this. We have one column for x of m minus 1. M is still indicating the width of the integer. Y subscript m minus 1 is the most significant bit of y. And then D subscript m minus 1 is the most significant bit of the difference. Okay. If you want to simplify what you're writing down, you can also say these are the sign bits of x, y, and d respectively. Okay. So now we also want to know, do we have an overflow situation? In other words, is the sign of d not making any sense? Okay, that's what we're trying to determine. So x, y, the most significant bits of x, y, and d are independent. Okay, they're not truly independent, but we can end up with all 8 cases. So we'll just kind of say that they are independent. So now you have a table of 8 entries. Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then finally we have 1, 1, and 1. Okay. So I just turned this into kind of like a truth table of sorts. Okay. So now the first question is, if I subtract a non-negative value from a non-negative value, this is row 1, can I end up with a result that is non-negative? In other words, 2 minus 1 is 1. Can that happen? Yeah, okay. So there's no overflow in this case. I put a stroke across the 0, because just want to make sure that this is an O and this is 0. 0 means false. Okay. So how about the next one? I start with a non-negative value, I subtract a non-negative value from it, and the result turns out to be negative. Can it happen? 1 minus 2 is -1. Okay, yeah, it can happen, which means there's no overflow. On this one, we are starting with a non-negative value. We subtract a negative value from it, and the result is non-negative. Does that make sense? It makes sense. That's the only way it can happen, actually. So that makes the next one not make any sense because we start with a non-negative value, we subtract a negative value from it, and somehow the result is negative. So this one is an overflow situation because the sign of the difference does not make sense. Next one, we start with a negative value, we subtract a non-negative value from the negative value, and the result is non-negative. Does that make sense to you? It should not make sense, right? So because you're in the red already, and I take away even more money from you, is it possible that you end up not in the red as a result? Should not happen, right? So this also should not happen. So without explaining and spelling out every single case, I'm just going to tell you the other three cases are possible, so we do not have an overflow situation. Are we good? So now what we want is to have an equation of some kind because we want to define overflow to be some kind of Boolean operation of xm minus 1, ym minus 1, and also dm minus 1. How do we do that? It's a technique that we have seen already, okay? When we try to figure out I think there were a few cases when we tried to figure out the R function for addition, we used this trick already. Okay, so the trick is if I want this row, okay, if I want row 4 to be a 1, but only that, okay, given that x m minus 1 is a 0, y m minus 1 is a 1, d m minus 1 is a 1, how should I structure that expression? So to make this one row, a 1, but every other row would be a 0, you have to negate xm minus 1 first, and then you end it with ym minus 1, and then you end it with dm minus 1. So this conjunction is going to be 1, but only for the fourth row. Okay, for all of the other rows, this expression is going to be true. And if people are asking, that looks like a multiplication, why did you say conjunction or and? How should I answer that question? When did we talk about the notation of conjunction? Day one of this semester. Okay, that was the first class. Okay, the first class, in the first class, we kind of talked about the notations. So this is and. Okay, so this is the negation of xm minus 1 and ym minus 1 and d of m minus 1. So do not, you can still look at it as a multiplication. That still works because we only got zeros and ones, right? So if you have any zero in the multiplication, the whole thing is going to be a zero. So it still kind of works out, but it is a conjunction. So that means for the next row to become a 1, we kind of have to do exactly the opposite, which is we have to take x of m minus 1 as is, and the negation of y of m minus 1, and the negation of d of m minus 1. So each one of these expressions, okay, this one and also this one, will only make the corresponding row a 1, but it will be false for all the other rows. But since we want the overflow to be a 1 for both of these rows, so that means the equation that we need is a disjunction of the two. Okay, so I will try to do something that is obscenely lazy, which is to copy and paste. All right, so we are going to copy and then paste and place it right about here. Cool, I like that. And then we'll make a copy of this too. Same thing, copy and then paste over here. And we can space it a little bit. Okay, very good. And then we just have to go back and say this plus here is not an addition because we use plus to also mean or in this case. All right, so are we good so far? There's an overflow flag, and this is how we define overflow. If you're wondering, whether we should perform the plus first or not, you know, implicitly we have parentheses around these. All right, so we are almost done, okay? Because now we go like, if there's no overflow, the sign bit is going to correctly tell us whether the signed value of x is less than the signed value of y, okay? But if there's an overflow, then the sign flag will tell us the opposite of what it is supposed to be. Okay, so that means in order to tell whether x is less than y, we kind of have to look at both at the same time. So we'll start a new page here. So now we have the sign flag, which is really just d of m minus 1. That's the sign flag of the difference. And then we have the overflow. Okay. Now, once again, these two are not fully independent, but for our discussion, we'll just kind of pretend that they are independent. So we have four cases to consider. Okay. When the overflow is a zero, meaning there's no overflow, whatever d of m minus 1 is telling us is correct. So I'm going to use a L flag here. Okay, so the meaning of the L flag is it is a 1 if and only if the signed interpretation of x is less than the signed interpretation of y. Let me say that one more time. The L flag is going to be a 1 if and only if the signed interpretation of x is less than the signed interpretation of y. You don't really have to write that down because it is actually in the notes. So I can point out to you. Okay, I'll do it now. So in the notes, if you scroll down to about here, it this is what it is telling you. So the L flag is a 1 if and only if, okay, right here, the L flag is a 1 if and only if the signed interpretation of x is less than the signed interpretation of y. So that is the conclusion is already given to you, okay? And I'm not gonna quiz you on the derivation, okay? So based on this, I think we know how to fill in that table, okay? So let me switch back to the tablet, and we're gonna fill in that table. All right. So we are basically saying if there's no overflow, meaning this row, the first and the third row, then d of m minus 1 is the correct answer. Okay, cool. Just copy d of m minus 1 as they are. But when there's overflow, which is the second and the fourth row, then d of m minus 1 is telling us the exact opposite of what it is supposed to be. So that means for row 2, since the sign flag is telling us it is not less than, but because it is an overflow, that means the actual answer is less than. And then for the last row, kind of the same deal. The sign flag tells us it is less than, but since we also know it's an overflow case, that means the sign flag is telling us the exact opposite of what it is supposed to be. So if the sign flag says yes, that means the answer is actually no. So this is a truth table that basically says your L can be defined as d of m minus 1 exclusive or with the overflow flag, which is actually what I wrote in the notes. So in the notes, it also mentions something about the S flag. S stands for sign. Okay. So the question is, what exactly is the sign flag? The sign flag is really just a fancy name for the most significant bit of the difference. And that's it. You have everything that you need to get the lab done today. All right. So let me see if there are questions. You can ask the question in a way that is concrete. So you can give me an example and you ask, how do we figure out which bit pattern is less than the other bit pattern? So does anyone want to give it a try? Yes, sure, absolutely. So give me two bit patterns. 0010. Like that? Okay. Okay, so let's do the subtraction first. So once again, I'm not going to explain the mechanism of the subtraction, but we'll focus on the flags that we end up with later. So 0 minus 0 is a 0, 1 minus 1 is a 0, 0 minus 0 is a 0, 1 minus 1 is a 1. Now we get onto the borrow flags. 0 minus 0 has no borrow. The 0 minus 0 has no borrow, so there's no borrow here. 1 minus 1, so there's no borrow here, no borrow here, and also no borrow here. And then for the D row, we have 0, 0, 0, 1. Okay, so I'm not going to explain this part, but I do want to label the rows just so that we know which row is which one. Okay, all right. So where's the borrow flag? The borrow flag is T of 4 because we count from 0. Okay, so this is our borrow flag. Okay, so I'm going to label it. This is the borrow flag. So according to this, because the borrow flag is a 0, I don't even need to do any type of conversion. I know because of this, I know VU of x4 is less than VU y4 is false. Okay, so now what do we do with the signed value? So for the signed value, this is x of m minus 1, the sign bit of x. This is the sign bit of y, which is y subscript m minus 1. And this is s, okay, the sign bit itself, which is also known as d of m minus 1. So now we plug that into the equation. But first of all, we just identify this one as the s flag. So now we look at the overflow flag. The overflow flag is going to take um, the negation of x. Okay, so let me just write out the entire thing and then we'll go ahead and fill it in. I probably have switched the order of the OR, but that's okay because OR itself is commutative. Okay. Okay, so we put this one here and here. This 0 goes here and goes here. And then this 1 goes here and it also goes here. Are we good so far? But we have to remember we have to negate this 0 and negate this 1, and we also have to negate this 1. So now we have a 1, we have a 1, we have a 0, we have a 0, we have a 0, and then we have a 1. Now remember, these are all ANDed together, and in between these two, these are ORed together. So now we end up with a 0 or a 0. So that means from the perspective of the overflow, it is also a 0. So once we have the sign and the overflow, we can now compute the L flag. So the L flag is the sign flag over exclusive OR with the O flag. So in this case, the sign flag is a 1, exclusive OR with the O flag, which is a 0. So the result is a 1. So that is concluding, because the L flag is a 1, it is now concluding that VS X4 is less than VS Y4. I don't even need to know what VSX4 or VSY4 become. I don't care about the value because I just need to know whether X is less than Y. And we have the conclusion, and it is correct. Okay? So is that kind of helping to illustrate how we pick out all the individual bits and figure out the answer? Yep. Okay. Um, does anyone want a second example? This one is good. Okay, I like this one because it is not less than from the unsigned perspective, but it is less than from the signed perspective. So that's good. Does anyone want to try another bit pattern? Yep, go ahead. Uh-huh. Say again. Uh-huh. 1100. Okay, sure. So this is X, this is Y, this is Q. Q is the exclusive OR between the X and Y. So there's a 0 here, a 1 here, a 0 here, and then a 1 here. And then we put a T0 as a 0. So there's no borrow here, there's no borrow here, there's no borrow here, but there's one borrow here. And then when we look at the exclusive OR between the Q and the T, we have the D row. So we have a 0 here, a 1 here, a 0 here, and then 1 here. Okay? So now we look at the conclusions. Okay, because of the b, okay, b equals 1 is telling me that vu x4 is less than vu y4 is true. Okay, well, does it make sense? X is representing 6, y is representing 12, 6 is less than 12 is correct. Okay, so now we look at the other one, the harder one. Okay, so we go back to the overflow flag. So the overflow flag, sometimes I use OV just to make it clear it's overflow. Okay, so for this one, we go back and look at the equation. It is the negation of x of m minus 1 and y of m minus 1 and d of m minus 1, or x of m minus 1 and the negation of y of m minus 1 and the negation of d of m minus 1. Okay, so now we plug in the actual values. Okay, this is x of m minus 1, so that's a 0. We are reusing the 0 over here. This is y of m minus 1, so we put that 1 over here. And then this is d of m minus 1, so that is going here. It's also going here. But then we also have to remember that x of m minus 1 is actually negated here. And then here, the y and the d are negated. So now we evaluate a conjunction. So this is 1 and 1 and 1. So the result is a 1 here. I really don't have to do the other one because if one side is true, or the whole thing is guaranteed to be true, but might as well do the second side too. This is a 0, not 1 is a 0, not 1 is a 0. So the conjunction is definitely a 0. 1 or 0 is a 1. Okay, so we know overflow is a 1. So if overflow is a 1, this is our sign flag, right? And then what is the L flag? It is the sign flag exclusive OR with the overflow flag, okay, which in this case is a 0, exclusive OR with a 1, which is a 1. So that tells me that, um, did I make a mistake somewhere? Mm, I think I made a mistake somewhere. Huh? See, oh, S is 1. Yeah, you're correct. Okay, let me go back. So I can tell that I made a mistake because the sign interpretation of x is not less than the sign interpretation of y, so I know that something is wrong. So this is a 1. I've copied the 0. Okay, there we go. So 1 exclusive or with 1 is a 0. So that tells me the sign interpretation of x, which is 6, is not less than the sign interpretation of y, which is what in this case? We have a 4 minus an 8 from it is negative 4. So 6 is not less than negative 4. So it comes to the correct conclusion too. All right. Any other? Yep, go ahead. That is correct. Not only that it does not make sense, it is opposite to what it is supposed to be. Yep. All right. So are we okay so far? Okay. All right. So we still have about 12 minutes to go. So are there any questions about this topic that you want me to clarify? Because we just went through a few actual examples, and I hope that will help you in your lab because this is actually procedurally how we do this. Okay. So are there other questions in terms of your concept questions? No concept questions? Okay. So if there are no questions, I am going to at least give you an idea of what we'll be talking about next Tuesday. So if you go to your notes here, we are done with two's complement. That was the lab on Tuesday. And then if we go forward, the next topic is called floating point number representation. Okay, so that's a pretty big topic, on next Tuesday. I definitely would recommend you to read a little bit about that before class. But since we do have 12 minutes or about 10 minutes right now, I am going to get into this also. But before I do that, well, okay, let me not do that. All right, so this is about floating point representation. So, floating point representation, and since I have my tablet up and running, so today is kind of great, okay, because I did not use the whiteboard at all. So that means if you watch the video, you actually get everything that we talked about today. Okay, so that's why I'm using the tablet. Cool. All right. So, okay, I need to show the tablet. It's really great that the tablet and the PC are talking using Wi-Fi. So I can just kind of walk around and, everything I draw here will still appear on the projector. Okay. So the first thing that I need to talk about is the scientific notation. How many people know what that means? Okay, we got a few hands. Okay, so the scientific notation means, okay, I'll give you a scientific notation in C++. Okay, so let's just say we have 1.23 with a lowercase e and then 4, 5 here. Okay, so the value that is actually represented by this expression is 1.25 times 10 to the power of 45. Okay, so the value of this is 1.23 times 10 to the power of 45. This is called the exponent, and this part is called either, okay, I shouldn't say either. In this case, it is both the coefficient and also the mantissa. Okay, so I can give you another number that has a coefficient but not a mantissa. So we'll try another one. We'll just say, zero point 0.5 of a billion. Okay. Ah, so zero point 0.5 of a billion looks like this. Okay, because 1 billion is 10 to the power of 9. So when you have half a billion, this is one way to say it. But in this case, the zero point 0.5 cannot be considered as a mantissa anymore, but it is still a coefficient. So this value is still zero point 0.5 times 10 to the power of 9. So what makes a mantissa a mantissa? When a coefficient is greater than, okay, so this is, okay, so when the coefficient is greater than 0, actually, I take it back. It has to be greater than 1. This is the coefficient, which is the number before the e, but it has to be less than the base. So because we're dealing with base 10, that means it has to be less than 10. So 9.99999 still makes a good mantissa. But as soon as you get to 10, it's not a mantissa anymore. It is still a coefficient, but we cannot call it a mantissa anymore. Are we good so far? Yes? All right. So now we move ahead and kind of talk about. I want to remind you about base conversion, okay? But this time the base conversion is about base 2. So we are converting a base 2 number to its value, to the value that is being represented. So, okay. So we're going to look at this as a base 2 number. What is the value represented by this binary number? It has a decimal point, which should be called a binary point at this point. So it has a binary point. What is the purpose of the point? What is the point of the point? It tells you where digit 0 is. Okay, so digit 0 is the digit that is immediately to the left-hand side of the decimal point. So that means this is digit 0 right there. Okay, so the value being represented here, okay, so if this is a 2 to the power of 0, this would be 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So we have an 8 plus a 4 plus a 1 plus, oh, what happens to the digits to the right-hand side of the point? Negative powers of the base. Okay, so this is representing the quantity of 2 to the power of negative 1, 2 to the power of negative 2, 2 to the power negative 3. So now we don't have a half, but we do have a quarter, okay? And then we also have an eighth, like so. Are we okay so far with this? This is nothing new, okay? When we talked about base conversion, we already talked about this part, okay? So now we just have to do some addition. So we have 8 plus 4 plus 1, which is a 13. And then we have a quarter plus an eighth. So that will make it a 0.375. That's it, okay? Are we okay so far with understanding what value is being represented by 1101.11? Are we good? How do we show? Oh, okay, I see what you mean. So in terms of the internal representation, how do we know where the dot is, right? So we'll get to that later, okay? We'll get to that later. Um, Basically, that point is implicit, okay? It is an implicit point. So let me get to the note first, okay? So let me go back to the notes, because in the notes, there is a equation that defines the value being represented by a floating point number, and this is that. Okay. All right. So I know it looks kind of ickish. Okay. Um, so especially just this part. Okay. Only this part is really useful. So if we look at F as a bit pattern, a 64-bit pattern, do we know how to interpret this? Okay. I know it is hairy to evaluate, but do we understand what the expression is trying to say? That is the question. Okay. Even though it looks kind of hairy, um, this is negative 1 to the power of 6f with a subscript of 63. What does that mean? F is a bit pattern, is a 64-bit pattern. What does F subscript 63 mean in that context? What do we use subscript for in this class? It has been very consistent. X subscript 0 is bit 0. X subscript 5 is bit 5, right? So F subscript 63 is bit 63 of a 64-bit number. It is the leftmost digit. Okay, all right. Um, I know this sigma notation has some really kind of wonky range for I, but can we evaluate that? Well, I is over here, so I starts with negative 52. So the very first F bit is actually going to be F0. It's going to be bit 0 of F. What do we do with bit 0 of F? We multiply that by 2 to the power of negative 52. We put it into the sum, and then we move I up by 1. It becomes negative 51, and so on and so forth. And then it will finish by I being negative 1, which means we'll be looking at F of 51 because 52 plus negative 1 is 51. But that particular bit, which is either 0 or 1, is multiplied by 2 to the power of negative 1, which is also known as 1 half. We just have to add up a whole bunch of those products, okay? That is what the middle part here is trying to say. Is that okay? So individually, each piece should be understandable, okay? We are only using symbols and concepts that we have talked about so far. What about the last piece? This is 2 raised to the power of this kind of long expression here. But that expression looks a little bit hairy, but it's not, okay? Because when you look at it, this is kind of the same deal, okay? I goes from 0 to 10. What are we going to do when I equals to 0? We use I to find a particular bit in the bit pattern F, and then multiply that 0 or 1 to 2 to the power of I, which is 0 in the first iteration, and then we just kind of go up in the loop. So that's going to give us a unsigned number. It's going to give us a non-negative number. What do we do with that non-negative number? We subtract 1023 from it. So the difference becomes the power of 2 that you need to raise to. And then when you figure out each individual piece, okay, You multiply the whole thing together, and guess what? Now you have just found out the value being represented by f as a 64-bit pattern. This is also known as the IEEE double precision floating point number format. Okay, so if I have to summarize the entire module, this is it. Okay, so next Tuesday, I will give you some examples. Okay, so I will go in both directions. I will say, this is the value that I want to represent. What does it look like as a double precision floating point number? And then we can also go the other way. Okay, this is the bit pattern. What value is it representing? So we can go in both directions. Okay, but it definitely helps. Okay, if you just kind of read this section a little bit first, make sure that you can understand this expression. Just because it is ugly to evaluate doesn't mean that you cannot interpret what it means. Okay, it just means that if you interpret it, it's going to be tedious. Okay, so that's for next Tuesday, and I will give you the access code of tonight's lab right now. So tonight's lab is subtraction and compare. And then the access code is, I think it's negative, but I cannot be 100% sure. Nope, it is flags. Lowercase flags. FLAGS. All right, I'll see you guys in the lab. Oh, you got almost the same phone that I do. Let me stop the recorder first.